everyone, my name is Hedieh Ahmadi and the other author of this paper is Dr. Hasheminejad. I am a master's student at Al-Zahra University, Department of Computer Engineering. The title of this paper is a new time series approach in churn prediction with discriminatory intervals. This is the outline of this paper. Let's start with introduction. When customers leave a company due to some reasons, we consider them as churn customers. Churn prediction is the process of identifying these customers tends to churn before they leave the company and convince them to stay. For companies, attracting a new customer costs 5 times more than maintaining an existing one. Because of this cost, churn prediction is important for companies. Several articles on customer churn prediction use classical models such as logistic regression and random forest, which usually aggregate all non-user information over a period of time into a single data point or non-sequential data. In this article, we propose an approach to use the time dimension of customer behavior. Since most of the techniques presented in churn prediction are classification models, we introduce a new time series classification to find churn customers. We can categorize time series classification approach in 8 groups. Distance-based. These algorithms use special distance functions of time series as the basis for classification. Dictionary-based. These algorithms find words in time series by using sliding windows, then calculate the distribution of those words to classify them. Shapelet-based. The focus of algorithms in this category is to find short patterns for each classes. These patterns are called shapelets and they are phase independent. Spectral-based use attributes in frequency domain. Interval-based. Instead of using the whole series, these methods explore sets of discriminatory subseries. Kernel-based, this algorithm using random convolutional kernels and transform the input time series. Then the transform features are used to train a classifier. Hybrid. These are an ensemble of various methods mentioned before. Most of the algorithms in this category are more accurate than the others. Deep learning, inception time and residual network are deep learning algorithms. Other purpose approaches are usually compared with these methods. Because we use transform kernels in our purpose method, we can consider our purpose method in kernel-based category. I will describe our purpose method in the following 4 steps. Data preprocessing. Data preprocessing, we use the retail transaction dataset. It is an open source dataset on Kaggle. This dataset consists of customer and date level transaction for few years. Transaction data provides customer ID, transaction date, and amount of purchase. Because the membership time of each user in the database is not known, we only consider users who made a transaction on the first day and are sure they are members. We have labeled the dataset to churn and non-churn by time window. When a customer does not use a service for a certain period, this approach labels the customer as churn. We considered a 1-year time window threshold. If customers did not have a transaction for a year, labeled as churn. For the train test split, to show that both train and test sets have the proportion of example in each classes, a stratified train test split was used. The train set is imbalanced because the number of customers with churn labels is less than 20%. We use a smooth to balance it. The next step is selecting discriminatory intervals. A time series is considered as a sequence of numbers, and we select a split point randomly on it. We divide each of the left and right parts of this point separately into two equal intervals. For each of the two intervals, based on the aggregate function, we calculate interval features. For example, as you can see in this figure, we calculate the mean of all the samples in that interval. The two newly obtained feature sets M1 and M2 are used to score the intervals based on a feature selection metric. Each interval with the highest score is selected, then recursively divided into two parts. This process is continued until the length of the interval is not less than 4. In this paper, we use 7 aggregate functions, consist of a slope, mean, median, standard deviation, interquartile range, maximum, and minimum. After all essential intervals from each aggregate function are obtained, we calculate the frequency of each interval or the number of times appear in all functions. The one or more intervals that have the most frequency among others are considered discriminatory intervals. We use two feature selection metrics separately, feature score and mutual information. Feature score has the advantage of fast computation, and it was used in other papers as a feature ranking metric. Mutual information measures non-linear relations between two random variables. It shows how much information can be obtained by observing a random variable from another one. The formula of mutual information for two discrete random variables is shown in this equation. In this equation, Px and Py are the marginal probability density functions, and Pxy is a joint probability density function. We rounded the results of each aggregate function to one decimal and ignore minor differences for using mutual information. The next step is data transformation. In this paper, we use convolution kernels to transform these discriminatory intervals into a new feature map. Kernel parameters weights, bias, deletion, and padding are set randomly. The kernel weight is randomly sampled from a normal distribution, bias is sampled from a uniform distribution, and deletion is sampled based on an exponential scale. Padding is randomly decided to be used or not. When applying the kernel, zero numbers are added to the start and end of the time series. If padding is used, the kernel's length is 2. If we fix the length of kernels, deletion is set to 1 for all kernels. The number of kernels is a hyperparameter. It is a trade-off between accuracy and computation time in setting the number of kernels. Our approach experimentally obtained that if the number of kernels exceeded 100 kernels, the accuracy does not change significantly. Hence, we set it to 100. By max pooling, we compute one aggregate feature maximum value from each feature map. The number of features obtained from each time series is calculated as this shown formula. For example, if the number of obtained discriminatory intervals is 2, as discussed previously, we use 100 kernels and one aggregate feature max pooling. The number of features will be 200. Since the kernels are used as a transformer, we call these features transform feature. In classification step, the transform features obtained from the previous step are used to train a classifier. In this study, we use SVM and ridge regression. In our proposed method, the split point is randomly selected and the results are depends on it. For decreasing variance in result, we considered an ensemble of 25 classifiers. Each classifier is built as mentioned steps with a random split point. To achieving the final result or label, a simple voting method is used, and the label with the most frequency is selected. The ensemble components have the same classifier, SVM or ridge regression. The results are evaluated in this section. As shown in the table, the example result of SVM with linear or RBF kernel and ridge regression with two different feature selection approach, feature score, and mutual information. We have reported the average result of 30 times run for regularizing classifier hyperparameters. 10 for cross validation is used. As you can see in this table, the SVM linear classifier with mutual information feature selection is the best among other. This algorithm has been considered as proposed method for comparison with other algorithms. As you can see in the left figure, the average accuracy of our proposed method is evaluated with other time series classification algorithms. The average accuracy is lower than some algorithms, but as we mentioned previously, our proposed method is in kernel-based algorithms. Because of using transformation kernels, the results have shown that our algorithm's average accuracy is better than the kernel-based algorithms, like Rocket, Mini Rocket, and Arsenal. In the next figure, our proposed method is evaluated with other time series classification in the sensitivity metric. Because in our problem, finding the customers is churner customers is important, we use this metric. As shown in this figure, our method is better than other algorithms. It means that our proposed method finds more truly churn customers. Compared with left figure, RISE algorithm has the best accuracy, almost 88%, but finds few truly churn customers, and its sensitivity is 25%. The evaluation of algorithms based on a recall metric is in the left figure. We separately compute recall for each class, churn and non-churn. The average result is considered. Our algorithm is the best among others. It is almost 8% better than the last best one. Based on the precision metric in right figure, we calculate each class precision separately and average the result. Our method is in the first place. The F-score metric is used to evaluate algorithms in the left figure. Our method is placed after DRCIF with the minimal differences. The average sensitivity versus training time of the algorithm with less than 10 minutes of training time is compared in right figure. As shown, our method reaches the best sensitivity with sufficient training time. At the end, our algorithm finds more customers that truly churn. The sensitivity is almost 16% better than the last best one. In addition, our approach has the best accuracy among the other kernel-based time series classification algorithms. This result shows that the selecting discriminatory intervals has a positive effect on accuracy. Our training time is less than 1 minute, which considering the sensitivity, it is the best one. Thanks for your attention.